Just a quick check, everyone, if you can see me, if you hear me well, and you can see my screen well. Is everything okay? Can anyone just voice out?
Yep.
All right, nice. Yeah. Okay, let's get this started. Thank you, everyone, for joining the meetup tonight. And before we get this started, here is a quick reminder on this overall event etiquettes. Please mute yourself if you're not talking, and by default, ask your questions in the gather chat. And what I can do is I can have that directed towards the speaker whenever appropriate. And as always, we are looking for speakers. And I have noted your response as part of the attendance registration, where few of you have expressed interest in delivering talk. And rest assured, I will directly reach out to you and get you lined up for the upcoming meetups itself. Yeah, thanks for your response. So thank you, AWS, as usual, for sponsoring all the logistics what is required for running this event tonight. So you can connect with this community in multiple ways. One, basically this meetup page where you get to know all the events which are being organized by this group of community. And second thing, to collaborate with the community itself, where you can join our Slack channel to interact with the community itself. So before we look at the agenda, here is an announcement for the event today. So there's going to be an AWS credits giveaway, which is expected to be broadcasted at the end of the event. So do continue up until the end of the talk. So and you will be given the forms where I will be passing over the credits later at the end of the day itself. So here is the agenda for tonight. So we have Darin, who's the Director of Technology from Imply. He will be talking about the rise of immediate intelligence on AWS. I'll kindly request and let Darin to self-introduce himself, part of his talk, and likewise for Kang and Nikit. So the second talk will be on demystifying the data transfer charges in AWS by Kang. And third and final talk will be by Nikit on chaos engineering in action using AWS Fault Injection Simulator. So before any further wait, we can get this event started. And before I pass over the controls to Darin, so there's a quick, note on some of the gather objects. So basically, for those audience, you can see the spotlight icons, couple of spotlight icons on your left, couple of spotlight icons on your right. So whenever you have a question you want to directly interact with the speaker, as we do so, you can come up to the spotlight icon and you have yourself unmuted so that you will be heard by all of this event participants itself. So you can directly interact with the speaker and you will be also heard by the rest of the audience. And for the speakers, when you intend to deliver a talk, you walk up to the podium and the place where I stand now. Yes, exactly the place where Darin is also standing now. So so you come here, and by standing here, this is again a spotlight area, so that you will be here by all of this audience itself. So come here, unmute yourself, start your screen sharing, and you will be here by the complete room. So without any further wait, and I'll pass it over to you, Darin. The stage is all yours.
Fantastic. All right. Hello, everybody. So, as Badri kindly said, my name is Darin Briskman, and I am coming to you live from Portland, Oregon. So, I am in your distant past. It is so early in the morning that the sun has not come up yet over the beautiful snow-capped volcanoes of Oregon. So, if I fall asleep during the presentation, you could just go on to the next person. I think we can do that. But I am from Imply, and if you're not familiar, Imply is the company that is founded by the creators of Apache Druid, which is a great open source package for analyzing streams, large data sets, actually data sets of any size for interactive conversations. So what I'm going to do is spend a little bit of time talking about what is this Druid thing and how does it work in the AWS world. So feel free to throw any questions you want to either into the chat or just yell out and interrupt me, and we can do that. So Badri, I'm supposed to go for about 25, 30 minutes. Is that the plan?
You're right, Darin. Yes.
All right, awesome. Then I shall. So let's start with what is Druid? So Druid is a database for modern analytics applications. So we're coming up, actually, we just went past our 10th anniversary. So it was created back in 2012 and has since grown into a pretty large community. So there's more than 400 contributors. We know, like any open source, it's hard to tell exactly how many people are using it, but we know it's well over 1,000. And we know that in the community, there's more than 11,000 people who are active, who have within the last 60 days submitted comments or submitted code or somehow done something actively in the community. So it's certainly something that is there and pretty good size. It gets down to why do I want yet another database, right? Because there's no shortage of databases in the world. In my past life, I used to be a product manager with AWS, where I helped with the database analytics and machine learning. And we had
What?
40 databases just at Amazon.
No, I wanted to do 100%
There we go.
speed. I wanted to
Is
get
somebody asking a question, or are they just not on mute? I'm guessing they were just not on mute. Okay. So, why does the world need yet another database? Well, that was kind of the question when Druid was created. So the people who created this had a problem. They were dealing with large data sets, and they needed to be able to ingest 1 billion events in less than a minute and query 1 billion events in less than a second. Well, they tried doing it with things like Postgres and other relational databases. That didn't work. Then they tried doing it with NoSQL. So this is 2012. DynamoDB didn't exist yet, but HBase did. So they tried doing some things with HBase and some other tools, and that didn't work. So they did something that even they thought was crazy at the time. They made their own database, but it's actually worked really well. So there's essentially 3 big things that people are doing with Druid. And if you're doing at least one of these, then Druid makes sense to look at. So one of them is the idea of interactive analytics. Being able to do drill downs, deep data exploration, being able to click up and down and through at any scale and have a really good analytics experience. So a good example of that some of you may have be familiar with is something called Thousand Eyes, which is a service from Cisco. So this is if you have Cisco equipment, you can sign up for Thousand Eyes and get all of that data, all those logs, all that information that you've already been shipping back to Cisco for customer service. Now you can actually see that data and explore it and see what's in my network and what's going on and what's up and what's not up and what's on the current version of the Cisco patches and releases and so on. So there's about 180 metrics that it can look at for each customer. And at any given time, we have from 5 to 20 queries per second coming in all around the clock. And they're all happening at less than 200 milliseconds. And that's, a big part of what leads us into this next piece, which is high concurrency. So as you're probably aware, most analytics environments are not very concurrent, right? If you use something like Apache Spark, the concurrency is 1. So if I want to have more than one query at a time, I have to create additional Spark clusters. Now, Databricks, who have been advancing Spark, have made that a lot more concurrent. They can handle 6 queries at a time. Some other things like, say, Snowflake can can handle 8 queries at a time, and then they can cluster that out to 80 in a cluster. Redshift is even more concurrent now. They can handle about 10, and they can also cluster, so you can get up to a higher number. Well, Druid handles thousands of concurrent queries. It's designed for concurrency from the beginning. So great use of that is at Amazon. Now, we have a lot of people at Amazon that we know are using Druid. Several, but as you're probably aware, since this is an AWS meeting, Amazon can be a bit secretive. So the one unit of Amazon that's talked about this publicly is Twitch. And the idea here is Twitch uses this for the self-service analytics. So if you've ever gone on to Twitch, or if you're doing any Twitch streams and you're looking at the analytics environment that lets you know, how many streams am I running in my channel, how many people are watching those streams, how many people are commenting, and you're seeing all that in real time. That's about 70,000 queries a day. It's about 8.5 billion events that are coming in historical data. So there are a few tools out there to analyze a stream. Kinesis Analytics is a great example, which lets you run SQL queries against a stream, often really useful. Another good example, if you're in the Kafka world, is something called KSQL or KSQL DB, which lets you run queries against a Kafka topic. But what if I have lots of streams? And more importantly, I don't just want to query the stream and see what's happening now, but say, but how does this compare with what happened yesterday, or what happened last week, or even what happened a minute ago, or what happened average over the last 3 years? So Druid is about being able to look at that real-time data. And this is a big deal because in Druid, the streams are inherent. I don't land the stream in a bucket and then load it in. The stream goes right into the database. So it is immediately queryable. Whenever the event happens, we are sub-millisecond before I'm able actually to see that event and query it. But I can also pull in however much historical data I want. So that is data that I'll usually be pulling out of an S3 bucket or some other data source, or directly out of something like Postgres or MySQL. And then I can see a lot of stuff there. So there's a US retailer named Target, which is fairly large. They are kind of mid-scale retail. So in the retail, they're not a high-end store, but they're not a dollar store. And they are pretty wide. They have thousands of locations across US and Canada. They're using this for insight on what's happening on both their Target.com operations and their actual physical stores. So there's about 3,500 sources. So the amount of data, when you pull back about 3 years of data for them, it's about 20 petabytes. So a fair amount. 70,000 daily average users running about 50 queries a second. So given that size and scope, we can't quite hit 200 milliseconds. We're slowed all the way down to 600 milliseconds in order to hit that. So this is where Druid falls into the world. Is if I'm trying to do something interactive, drill up or drill down, or if I need high concurrency and at a good value, again, Spark, I can get high concurrency. Other things I can get high concurrency. It just costs a lot of money. Here it's built in. Or if I want to be able to have insights on streams and insights on historical data together, it makes a lot of sense. So one I'll mention that's fully open with this is Wikimedia. And if you go to Wikistats and look it up, you'll find this great interface that lets you see over time and pick a month or pick a day how many edits have happened on Wikipedia or Wikicommons, and drill up and down from different, how much is happening from Singapore versus Malaysia versus UK versus US, how much is on web devices, how much is on mobile devices, and so on. And that's all Druid, making it easy using this open source system. Okay. So what makes Druid so special is that it's flexible, efficient, and resilient. So it has a unique relationship between storage and compute. There's lots of independent components. So the data management, where data is ingested into Druid, it's whether it's streams or it's batch data, the data comes into Druid, it's split into columns, it's optimized, it's bitmapped, it's compressed, it's set up for very rapid queries. It's also made durable by storing it onto S3. So I'll have at least 2 copies in high speed in the Druid cluster and a deep storage copy, which means essentially it's continuously backed up. So I don't have to worry about backups. I always have the data there. I will never lose any data. That's where we get to the resilient piece. Even if I lose all of my servers, all that data is on S3. So I can always get my data back. And for streams, it's very good at exactly once semantics. So if you've ever done stream analytics, one of the big problems is if you're using something like Redshift to analyze streams, so you land those streams in a bucket and then you put the streams into Redshift. Did that stream hit the bucket? Sometimes you're missing events, sometimes you double count events. This can be a big deal. Obviously, if I'm double counting events, then I'm going to be throwing my analytics off. Well, with Druid, that's never an issue. It pulls the data directly out of the stream, no connectors, no extra software. Both the Kinesis and Kafka are built in. The data goes into Druid, and this is kind of the fun part. Once it's optimized the data and committed it into S3 for durability, then it uses exactly once to tell the stream, okay, I've accepted that one. So every event comes in once and only once. And again, even if I lose all of my servers, when I pull them back up, as long as I'm within that 7-day window of the stream, no problem. I can pick up exactly where I left off. Occasionally, we have customers test this in an unplanned way, such as the unfortunate outage of EC2 in US East 1 back last November. So we had a number of customers have a couple of hours outage when EC2 service went down for not all customers. It was mostly those in US East 1E availability zone. But we did have some customers who are running Druid in there, and they lost access to all their EC2. But a few hours later, when Amazon got the data center running again, no data was lost. So it's flexible, the unique components. It's efficient in that it optimizes the story in the query engine. It's massively parallel. So how do we do all these petabytes so quickly? The short answer is scatter gather. So it's going to take it's going to have the data distributed over many nodes. It's going to scatter those queries, lots of things in parallel, and then pull them back. And we've got zero downtime, zero data loss. Druid is designed that it never goes down, and there's never planned downtime. Any updates you have to do are all rolling upgrades. So, and the clusters can be of any size. I can add or remove nodes without any downtime. It all auto balances. So the smallest possible cluster is running on your laptop, and the largest cluster I know about is running on AWS, and I think it's 12,000 servers, 12,000 EC2 nodes. So, and that's not a limit. I just don't know of anyone doing it bigger. So we have the ability to really scale to any size. And that, gets down. Some systems share nothing so that they get better query performance. This is like way back when, so things like Informix were built on. Others have full separation of storage and compute to be more elastic. This is Snowflake's design. Druid actually does both. So we both are using that deep cloud storage. In the case of Amazon, of course, S3, but we're also ingesting the data. So a lot of what most commonly Druid is going to run on the data nodes of Druid are going to run on i3 nodes, so that I have that high-speed NVMe drive locally in order to have that optimized fast storage, as well as being able to call on the S3 storage when I need it. So we kind of get a best of both worlds with prefetch segments and clusters being able to grow dynamically. And then here's a bit of the query engine. So the query nodes are going to be a different process. If I'm in a larger cluster, I'll put them on separate machines. In this case, I don't really need local storage except for booting. So usually this is going to be on something like a C5 or C6, or sometimes M nodes in EC2. And then I'll be able to run that to manage the actual queries. So I don't need a lot of query nodes. And then I also don't need a lot of master nodes. Those are things doing coordinating processes and helping set, when I'm growing or shrinking the cluster, helping manage the auto balancing and so on. Those are usually pretty small. So those will usually be a cluster on usually an M environment or something along that level. So finally, as I do repeat, the whole idea of automatic recovery, except it's not failover. It just sees the damage and it works around it and heals. So here's a case of Druid with 3 data nodes, and one of the data nodes fails. Why did it fail? I don't know. Maybe somebody hit the wrong key. Maybe we had a server crash in EC2. Doesn't happen much, but it does happen. In any case, you don't have to do anything. The system will see that. it had already distributed replicas of all of the data segments across the other nodes. So it's going to see, okay, well, if I lost node 1, I need to make extra copies of these segments that I'm now missing. So I'll go ahead and copy those off of the, sorry, I lost node B, so I'll copy the segments off of A and C, make sure it's all covered. And if there's a segment that I no longer have a copy of, well, I can pull it out of S3 and load that back in. And then that's it. No failover needed. Now, later on, if I want to expand the cluster and put a third data node back in there anytime, I can add a third data node and it'll automatically balance across them. Or a fourth or a fifth, or so go up, go down, elasticity. Now, how does this work with AWS? Well, we have a number of things here. So one is, as mentioned, Kinesis and Kafka stream ingestion are built right in. So if I'm using managed service for Kafka, or if I'm using Kinesis, all I have to do is when I set up the ingestion work in Druid, say I'm subscribing to this Kafka topic, or I'm going to be a Kinesis sync, and here's the topics or Kinesis streams to which I want to subscribe. Batch data is all coming in from S3. So how do I get the data into S3 from the data sources? I can do that through all of the tools you have to use data into S3. So in Amazon tools, that can be Kinesis Firehose, that can be AppFlow, that can be Glue. Certainly, we're more than capable of reading a Hive Metastore. So, I can use Glue to set that up and it just reads it. Or I can use any other ETL tool that can land things in S3, right? Informatica, Matillion, Fivetran, whatever. And then, of course, the batch injection is from S3. And then finally, how do I actually visualize this if I want to look at pictures? So the example I was showing earlier is from Pivot, which is a tool from Imply. But I don't have to use Pivot. I can use anything that can use JDBC or ODBC visualization. So we have lots of people using Druid with Superset if they like open source, or Grafana. In the Amazon world, we have those who like doing it with QuickSight, or other tools like people in the Microsoft world like to use Power BI. Other people like Looker, Tableau, whatever you like as a visualization tool. And then how do I deploy this thing? Well, you have kind of three choices on how to use this. So one is what we call Polaris. Polaris is database as a service. So this lets you use Druid the same way, and this is from our company, Imply. So obviously, when I get to these deployments, this is what Imply is providing. So in addition to just the raw Druid, we're providing enterprise support, we're providing deployment. So if you use Polaris, it's fully managed service. So just like, when you use a fully managed service like DynamoDB or Aurora, we handle everything and all you have to worry about is the data. And that runs on AWS, and it is by the node. So you have, the usual t-shirt sizings of small, medium, large, extra large, and so on. And, pick how much capacity you want. We have tools to help you figure out, how much you need based on the amount of data you have and the amount of queries you want to run. The other side of the spectrum on the right here is Imply Enterprise, where essentially we give you Kubernetes containers for you to run. So here's the Kubernetes containers, really easy to set this up. So I have to admit, Druid is easy to use and it's really scalable, but it's a little bit complex to run. That's what Imply is for, is to make it easy for you to run it, because it's got lots of moving parts. We take care of those moving parts, hand it to you in containers, you set them up and run them. And this way, because it's your environment, it's your environment. We have no access to it unless you give it to us during a service call. And obviously you get enterprise support and, phone numbers and email to get rapid response. And then in between is something we call enterprise hybrid, because it's a hybrid of us running it and you running it. It's in your VPC. It's in your AWS infrastructure. But you're giving us the access and the passwords to have the people from Imply come manage it for you. And that happens to be our single most common choice that people have right now. So the Polaris is growing faster, but especially people who have larger environments or have special security needs, they like the idea of it's my VPC, it's my environment, I control the security, I control the access, but I don't want to run this software, so you do it for me. And so that's the environment we get. So if I look at enterprise hybrid, I end up with an environment like this. So the control plane will be on Imply's VPC, where we're doing configuration management and a front-end portal. but the data plane where all of the data lives is on your VPC. So that way you control the data node. So notice the master and query and data nodes we talked about, that's all sitting there in your environment. The metadata for, I should have mentioned earlier, sits on either MySQL or Postgres. And if you're doing it on AWS, that's a great use for RDS. So it's pretty small, but it's important. So we'll set that up in RDS. And because we don't want to lose that data, we'll set it up in RDS with or Aurora if you want to, but Aurora is kind of overkill for this. So usually we'll set it up in RDS with, automated failover and persistence, and of course using your S3 environment. And in our world, of course, we set all that up through not just Kubernetes, but through CloudFormation to make it easy to set up and configure and roll out the nodes. So all in there using the AWS components. And then what is Imply actually doing? Well, the base Apache Druid is open source. You don't have to use Imply for this. It's not hard to go right to druid.apache.org and download it and play with it. But if you're dealing with Imply, then we can give you the flexible deployment. So it can be fully managed or hybrid managed or self-managed. We're giving you the management tools and the performance monitoring. We're giving you the expertise. The people who created Druid are founders and senior people. One of them actually lives in Asia and is commonly seen around ASEAN and ANZ and Japan, named Eric Cheddar. But the original founders are all here with Imply, helping with this and the 24/7 support. And then there's a couple of tools that we make commercially available. As I mentioned, Pivot, which is an option for your visualization. And that's what a lot of people like Cisco have chosen to embed in their system. And whenever you talk to a vendor, they need to put up a screen like this that has lots and lots of logos of customers. We have lots of customers. Our best known customer in Singapore, of course, is DBS, which I'm sure you've heard of, and many of you might have DBS cards in your wallet right now. And they're using it for real-time fraud detection. So looking at streams coming in, and when you use that card in your wallet, is it you? And is it something you're actually buying? And is it something that should be allowed to be purchased, and so on? So I'm sure you're aware there's a lot of incentives for fraud in financial tech transactions. So we want to catch those and see them immediately. Very similar model done in the US by American Express and others. And then a lot of use in advertising technology, gaming, tech companies, security companies, communications, big retailers, people who are going to have streams and large data coming through. All right. So if you want to learn more about this, a few things to play with. So one is Imply Polaris is a free trial. You don't even need a credit card. We don't play games. Click on it, set it up, play with it, see if you like it. If you'd like to learn a little bit first or afterwards, go to Druid University. We have a whole bunch of free education videos that you can walk through. They include some great hands-on labs, so it gives you a chance to learn this stuff. Or join the community. Come to druid.apache.org and join our Slack channels and our chat rooms and other pieces. There's some links there if you want to look at some good case studies of how Pinterest is using Druid or how Netflix is using Druid. And of course, you get a t-shirt. So if you would like the t-shirt, just click on that link. We're not going to ask you a whole bunch of questions. Mostly we just want to know your name and your email address and where to send the t-shirt and what size t-shirt you would like. And we will happily send you a Druid t-shirt that will be a much more interesting t-shirt than the logo indicates on this slide. So with Druid. So with that said, any questions? Anybody still awake?
All right. Thank you, Darin. Any questions for Darin?
Oh, come on. What a quiet group.
Kenny, I'll probably get this going. Yeah.
Yeah, Kenny, you can ask a question or at least heckle me.
I'll probably get this going, Darin. So maybe let me understand. So you mentioned about the concurrency as the key of basically that the Apache Druid is a product. What it is came up for to improve to provide a lot more concurrency in terms of the analytics data in the analytics or what you use in this platform itself. Maybe what key changes architecturally you have done in the product perhaps the Druid as a team done in the product, which have enabled this sort of improved concurrency compared to the rest of the products itself, or compared to the rest of the solutions?
So it's really about this part of the design, and what I'm showing here is that I have multiple query nodes. So each query node can handle running multiple queries. And then each query node is going to distribute those queries across lots of data nodes. So I have two things going on here. One is that because the data is immutable and because the replicas, it's not like a world where I have a primary and a replica. It's like a library where I have more than one copy of a book. They're all the same book. So I could be running queries against the same data multiple times. Any given segment, right, which is essentially a file on the data node with a few hundred megabytes of the data, usually in a specific time segment, but can be other organizations. I'm going to have that. I can be running lots of queries against each of those data nodes, and then each query node can handle multiple queries. So I'm not going to say, if I'm running this on my laptop on the smallest possible cluster, I'm not going to get thousands of concurrent queries. But even on one machine, I can get 10 plus concurrent queries. And then as I scale up, I can add more query nodes, add more data nodes, and get that up to the hundreds or thousands or tens of thousands of concurrent. And it was built for that sort of concurrency. And I think you all know this from just systems architecture. When you build something to do something, it's actually not that hard to build it to do that. But if you come in later and say, hey, I have this database and now I want to make it concurrent, that's anywhere from very hard to impossible, right? Just like I can have a house or I can have an apartment building. But if I build a house and then later decide to turn it into an apartment building, that's really, really hard. So if you look back at why Druid was created, what it was created for, it was to be able to combine streams and historical data at high concurrency at very high speed. So that's what Druid is good for. On the other hand, it was not designed to be simple and easy to run. So it's not that hard to run, but it's a fair amount of work. And that's why Imply was created, to make it a managed service so that you don't have to run it.
All right.
Okay.
All right. Yeah.
I guess Badri is the only question I'm going to get.
Any other questions for Darin, guys?
Hello? Hello?
All right, then. Probably
Okay, awesome.
no further questions. Thank you very much, Darin.
So Badri, did you get the slides that I sent you?
I'll take a look.
Right.
I'll take a look and have that circulated. Darin, maybe do you mind going back to the final screen where you have announced for the survey link? I'll just pass it over to the chat here.
Absolutely. Or I'll put that in the chat myself.
Okay. Thanks.
All right. Fantastic. Thanks, everybody. And I look forward to the rest of the meeting.
Thank you, Darin. All right. Kang. Yeah. Awesome.
Badri, someone was asking question actually. Probably Ather. I saw his mic offline. He was probably, but it was quite slow actually, I guess.
Oh, really? Okay.
Yeah.
I thought do you still have questions for Darin? Or you did it mistakenly?
Yeah, I was just asking is like how are you able to hear me?
Okay. Anyways, you can pass on the question with the chat if you still have a. I thought, yeah. All right, Kang. Yeah, over to you.
Yep, okay. Can I just check if you all can see my
Yes.
screen?
Yeah,
Great.
perfect. Yeah.
Okay. So, hello everyone. I'm Kang, an associate consultant for Source Singapore. And Source has been delivering cloud at scale for over a decade, focusing on regulated industries such as FSI, aviation, and the public sector. And today's content is part of Source Serverless Training Program, and you can find out more through our website. And this, the content that I'm covering has also been published into the AWS blog on 14 March 2022. In this talk, we will be talking about how to calculate a better estimate of your data transfer charges in AWS. And we will go through two visuals created by Source Group to walk through scenarios in a server-based and serverless architecture. Note that all pricing that we are discussing here is for the Singapore region and in USD. So anyone who has worked with the cloud before will know that understanding the data transfer charges is not the easiest thing to figure out. There are just too many factors to consider, and the documentation for these charges are often not explicit or comprehensive enough to provide a clear understanding of all the associated charges. And there are a few things that needs to be considered. First, we have to understand the flow of the traffic. So in a typical request within the AWS environment, there are 4 flows to consider, and each may or may not incur charges. When traffic is sent from one service to another, we need to consider the flow of the traffic exiting the source, called the source egress. The traffic entering the destination, called the destination ingress. The returning traffic exiting the destination, called the destination egress. And lastly, the return traffic entering the source, called the source ingress. And there are different pricing options depending on where your data is going. So for example, data transferring into the cloud is almost always free. Data transferring within the cloud is sometimes free. And data transferring out of the cloud is usually not free. If the traffic is going to or via the internet, then this is usually the most expensive option. And many fully managed services have public endpoints to interact with them. And this usually means that your data is going via the internet. And the cloud consists of regions such as Singapore, Ireland, and Eastern USA. Data transferring between 2 different regions is usually not free. Within this region, there are 2 or more availability zones, and this can be thought of as different data centers. Data transferring between 2 different zones is sometimes free. And lastly, data transferring within a single availability zone is usually free. One more thing, the term VPC features a lot on this section, and those who are unfamiliar with it, a VPC is just a virtual network in the cloud where we can provision our resources. There are some other factors we need to consider when determining costs. For example, some cloud services may have their own pricing model for data transfer. And one such service is Direct Connect, a service commonly used by enterprises to connect more securely to the cloud. When traffic is sent through network services in your account, such as the Net Gateway or VPC endpoints, they have their own fees for the transfer, which could replace other transfer costs or add to them. And lastly, it's important to remember that each region has its own fee for the services that can be provisioned there. So to be clear, these service fees are not determined by where you are based, but by where the resources are provisioned. It's common to deploy development environments into cheaper regions in USA, for example. And this needs to be considered when determining the operational costs based on such a development environment, because the production environment, which will be local, might have higher service fees. So let's walk through the visuals mentioned earlier, and starting with the one that focuses on services typically used in server-based applications. And while this diagram may seem complex, we will walk through some examples to help you better visualize how it flows and understand the pricing involved. And before we start, here is a general rule of thumb for data exchange charges in Singapore. For internet traffic, all ingress traffic, that is, all traffic that is entering AWS from the internet, are free. Data charges for egress traffic going out of AWS, uses a tiered pricing model. And the first 100 GB is free, followed by 12 cents per GB for the next 10 TB and so on. For traffic that stays within the same availability zone, both ingress and egress are free. For traffic that stays within the same region but across availability zones, both ingress and egress are charged at 1 cent per GB. And lastly, for traffic that goes across region, ingress is free, whereas egress has a charge of 9 cents per GB. To help visualize the flow of traffic, we will use a typical web architecture that uses an application load balancer to load balance the traffic across EC2 instances that are hosting the web application. The web application uses Amazon RDS as its database. From the top of the diagram, we can see traffic coming in from the internet. Here, ingress traffic into ALB is free. ALB is one of the few services in AWS that charges based on a processing fee. And here we are chargeable at a rate of 0.8 cents for every GB that ALB processes. The request is then routed out of ALB to our EC2 instances, which is free. The traffic received by EC2 is also free. And since our RDS is in the same AZ, traffic to and from our EC2 is free. And when EC2 returns a response back to ALB, it is free. However, when ALB returns the response back via the internet data transfer charges apply, which could range between 8 to 12 cents. In our previous example, we talked about having the RDS within the same availability zone. If our RDS is in a different availability zone, we have to pay the intra-AZ data transfer charges. This would be 1 cent for EC2 egress, 1 cent for RDS ingress, 1 cent for RDS egress, and 1 cent for EC2 ingress. This data pricing is also similar if your EC2 talks to other VPC resources, such as EC2 instances. And now, if our EC2 talks to another RDS in a different region, the regional data transfer charges applies. Here, the egress for EC2 is charged at 9 cents, but the ingress for RDS is free. And when RDS returns the result, the egress is charged at 9 cents and is free for EC2 ingress. When our VPC resources interact with each other within the same availability zone, we must take note of the IP addresses that we are using. In this example, the data transfer charges between the EC2s are free if we are using private IP addresses. However, if we are interacting through public IP addresses, we will be charged the intra-AZ transfer charge, resulting in added cost. And there are some services that have a different pricing model than the standard ingress and egress, and CloudFront is one of them. Here, ingress traffic to CloudFront is also free. However, the egress charge from CloudFront to its origin is priced at 6 cents per GB. Ingress and egress from the origin is free, as is the returning ingress traffic to CloudFront. And when CloudFront returns a response back to the internet, it is priced between 6 to 12 cents on a tiered pricing model. And the good news is, as of 1st December 2021, CloudFront offers a free 1 TB of egress traffic every month. And there are some other considerations when trying to determine your data transfer charges, such as the networking services that you are using. And we'll be covering all of this in more detail in the serverless example. And now that we've gone through the server focus diagram, let's take a look at the serverless version. And compared to the server-based application, the data transfer charges here takes up a larger part of the total cost. And as such, understanding the data transfer charges for serverless is quite important. Lambda is a commonly used service in serverless for the compute layer. And it is important to note that all Lambda invocations are free, regardless of the availability zone and region. API gateway integration with Lambda is a common approach to exposing Lambda as an API. Let's look at the data transfer cost associated with doing so. Ingress internet traffic to API gateway is free, but the return traffic for API gateway back to the internet is priced at the internet data transfer rate of 8 to 12 cents. If our Lambda is in the same region as our API gateway, traffic between them is free. However, if our Lambda is in a different region, we have to pay egress charge of 9 cents for the API gateway based on the regional data transfer charges. As mentioned earlier, all invocations to Lambda are free, so there is no price associated on Lambda. Now, let's look at Lambda to Lambda interactions. While this is possible, this is an anti-pattern for serverless. If our Lambda is talking to another Lambda in the same VPC, there will not be any data transfer charges. Our Lambda interacts with another Lambda in a different VPC. The intra-AZ data transfer charge of 1 cent each for ingress and egress is built on the invoker. And if our Lambda interacts across region, then the invoker is charged 9 cents for the egress traffic. Now let's look at Lambda to Aurora serverless, a relational database. Here, if they are in the same AZ, all traffic is free. If they are in a different AZ, then there is a charge of 1 cent on all 4 flows. If they are in a different region, then 9 cents is built on the 2 egresses. And for Lambda to interact with external services, it needs to go through a networking service, each with its own pricing model. For the same AZ, all traffic is free between Lambda and the networking services. However, if it's across AZ, there will be an ingress and egress charge of 1 cent on the Lambda side. Do take note of the data processing fees for the different networking services. If you are using a proxy, then the standard EC2 charges will apply. Traffic through a VPC endpoint is charged at 1 cent per hour, whereas traffic through Net Gateway is charged at 5.9 cents an hour. When deploying Lambda, we can choose to also not assign a VPC to it. And in this scenario, AWS places Lambda in a AWS managed VPC. If the Lambda interacts with a VPC resource in the same region, then the intra-AZ charge of 1 cent on all 4 flows apply. If it interacts with a VPC resource in a different region, then the regional data transfer of 9 cents on both egresses applies. And if it interacts with other Lambda not in VPC, regional data transfer applies if they are in the same account. But internet data transfer charges apply if they are in a different account. And lastly, let's just look at some commonly missed data processing charges during cost of estimation. This is based on our experience and interacting with our clients. And this diagram shows a list of popular services and their associated charges, but I'll only be going through some of the more commonly missed ones. So the first is Amazon CloudWatch. And whenever we execute a Lambda function, at least 3 log messages are generated. 1 for the start, 1 for end, and last for a report. And these logs are stored in Amazon CloudWatch, which is chargeable at 70 cents per GB. And another service would be KMS. When our Lambda function tries to access services that uses KMS, there is a charge for each KMS request, which is easily overlooked. And when using S3, beside the associated storage costs, there's also a charge per request, which differs from the type of depending on the type of HTTP method that you are using. So for GET requests, it is chargeable at 40 cents per million requests, whereas if you are using put, post, copy, and list, they are chargeable at $5 per million requests. And this brings us to the end. And calculating accurate data transfer charges in the cloud can be challenging. And we hope that this visual can provide a better visibility and understanding of how the charges are calculated. And with this understanding, you can have a more comprehensive view of your total cost of ownership when moving to the cloud or when you are trying to estimate your costs. And if you have any questions, please feel free to reach out and post it in the chat. And you can also read more about this in our blog article by scanning the QR code. Yeah, that's it. Thank you.
There are some nice comments. You can take a look, Kang.
Yep.
Panadol.
So,
Yeah.
well, data transfer charges in AWS is always overwhelming. I think perhaps a lot of very good information, like it will help us to have a mental model on the data transfer charges. I think it's fantastic. Thanks for it. Thanks again. I can see a lot of work have been went in preparing this guide.
It was very informative, actually.
Yeah, very informative. Yeah, that's fantastic. Thanks for it, Kangson.
Yep, thank you.
Any question for Kangson?
Yeah, I see a question in the chat. So data transfer seems to be the biggest source of unexpected AWS charges. What's the best method to monitor data transfer to avoid an unpleasant surprise when the monthly invoice arrives? Right now, I think the best way for you to monitor data transfer charges is through AWS budgets and setting thresholds and alerts for when your budget is exceeding your normal consumption or when it's forecasted to be to overshot your normal consumption. And I don't, off the top of my head, I don't think there's any services that can really give you a calculator of sort to calculate your data transfer pricing. Although you can use the information that's on this blog to really try to have a rough gauge and create your own form of a calculator.
Yeah. Probably if I can add on, like, Darin, one of the service what we can look at it is the AWS Cost Explorer. The Cost Explorer, I think we can generate a report, but one caveat with AWS is like, I think it is still an end of the day report. Which with that information, I think we can do on sort of a forecasting with the charges what we can anticipate for for every
Yeah.
month. Yeah.
And one of the motivators for us creating this blog was because we do have similar challenges when trying to uncover all these data transfer charges, and
Oh, yeah.
especially when we were looking at serverless technologies and trying to play with Lambda, it
Yeah.
wasn't that explicit. Especially when if your Lambda is being caught, data transfer charges doesn't apply. So
Right.
we managed to uncover all this information through conversations with the AWS team.
I see. Perfect. Perfect. Nice. Nice. So there's a question from Ben. Is there a way to simulate it? Maybe Ben, maybe you can unmute yourself and you can elaborate your question. What simulate it? What do you mean by that? Yeah. Sorry, no mic. Okay, maybe Ben, what you can do, like, so there you can see the place where I'm standing now. So you can just come over to there and unmute yourself. Perhaps if you well, if you would like, you can also type in the chat with bit more elaboration here. Oh, never mind. Okay. Probably Ben, they can type your questions here. I think I'll direct this towards Kang. Yeah, Kang, perhaps if you don't mind, you can share the slides with this community. I think that will be also helpful. But as you feel comfortable here.
Okay, yep. I have your email, and yeah, I'll check and I'll send it to you.
All right. Sure. Yeah.
Okay, I think Ben has a follow-up. So we just
Yeah.
meant that an architectural level simulation or visualization, like what he was showing.
Yeah.
I think as of now, when we are creating this content, this was the best form of. We felt like this was the best way for us to illustrate how you could look at data transfer charges
Sure.
in a more visual manner.
Yeah.
So we did encounter several other articles that talk about data transfer charges, but they were mostly outdated already. So mostly in 2019. Yep. So I think for now I don't know of any simulation services that you can use, and this is just only this diagram.
Yeah. All right, then. Thanks a lot for sharing this, Kang here. Very much informative and helpful here.
Yep. Thank you.
Maybe. All right, then. I think Nikit, over to you.
Yep. Can you hear me?
Yes. Perfect.
Okay, cool. Let me just share my screen first. Hello. You guys can see my screen, right?
Yeah, we can. Yes.
Okay, cool. Hello, everyone. My name is Nikit. So today I'm going to talk about chaos architecture and chaos engineering with AWS FIS service. So let me just quickly put into presentation mode. Okay, perfect. So yeah, a little bit about me. Like currently, I'm working at SGX and I do cloud architecture and solutioning. I published two books. The first one was related to AWS Automation Cookbook, moreover on like the developer tools of AWS. It was published around like 3 to 4 years ago. So at that time, that service was quite new. I gave all the tips and topics like hands-on examples over there. The second book is Accelerating DevSecOps on AWS using Chaos and AIOps. It's a new book that has launched, I guess, 2 weeks ago. It uses all the latest AWS services around like your Proton, DevOps Guru, Code Guru, all those things. It also have like the new like the SAST, DST tools, everything over there. Apart from that, like I also write technical blogs and I contributed to open source projects. Yeah. So let's get started to the agenda. So today I'm gonna touch base the concept of chaos engineering and its availability model. I will also discuss different phases of chaos engineering. Then I will talk about like how AWS this managed chaos engineering service like is helping us to perform the chaos experiments. I will talk about its component, and then I will showcase a small demo, uh, and like I will perform some disruptive actions on Kubernetes resources, like deleting some of the pods and nodes, and we'll try to see the resiliency of the applications, right? Post demo also, like I will basically show you our architecture diagram, like how and at what stage we can actually put the chaos experiment, so that like it will be like a continuous CI/CD pipeline, as well as like you'll be having a chaos experiment in place, right? So we all love cloud and microservices, right? Like we are in this AWS meetup, like either you might be using AWS services or you are interested into it to use it, right? Because of its features, right? It's scalable, managed service. You just pay for whatever you are using. So like even financial industries, right? Like banks and all are also like embarking their cloud journey, right? One another thing is like since uh, people are moving towards cloud, the new applications as well as like the developers are developing, they are like moving towards microservice architecture as well, because of its own advantage, right? Microservice services are like language agnostic. It is easy to troubleshoot and all, right? uh, but in case like you have like if your application consists of like 10 to 50 microservices, you will be doing fine. You can easily test all the features of your microservices. So currently, like how are we doing that? So we have like unit test and integration test to build the confidence, like yes, whatever services we are running, it's working fine. We do unit test for individual services, and integration test like in case like we want to test like the multiple services together, right? But this we are talking about only at the application layer, right? What about like some sort of operational logics that application does not handle at some point of time, or it might handle as well, right? Like for example, if you put a latency, like a very high latency, there might be a scenario that one microservice is trying to calling to another, but the another microservice is not responding it, or it is responding so slow that there is like a timeout error, right? So these sort of situation, right? Another thing is like, what if our underlying infrastructure fails, right? That will happen to the application, that like it might not work. I mean, we do design a very, like AWS have this well architected framework, right? Like whenever we deploy any application, we always make sure like, yeah, there will be HA, like there will be multiple AZs. But I mean, how many of you guys are like really trying to test this HA thingy like in your production servers where the actual application users are using it, your application, right? We definitely do a POCs like, okay, yeah, auto scaling is working fine. Like load balancer is working fine. Okay, yeah, I mean, like in case like there is a more traffic, like auto scaling group is like able to spin up the new instance. But have you ever tried to, like break down things into your production servers? Like, I mean, definitely a lot of guys will say, oh, yeah, my architecture is like very well proof and it can handle things. But apparently, whatever we think, maybe like it does not happen, right? Like that's why there are like outages, right? And like in this world, like if you are having any sort of outages, like there will be a business outcome, like you might face any losses, like even a small amount of latency. For example, like we use all this e-commerce, right? So the people mindset is like that, right? If there's like a Black Friday or any sort of sales, right? Like if you are using one website, for example, in Singapore we use Lazada, right? If you will be facing that, okay, yeah, the Lazada page is loading slow, people may just move towards Shopee, right? Like so there might be like a business impact over there, like there will be a sales drop as well. So these kind of things is like like giving a low confidence is like, okay, yeah, I mean the system like we designed, but it is not working perfectly fine, right? So to avoid like these sort of outages, we do chaos engineering, right? So basically the normal test is not enough. We need like something apart from that. So we do chaos engineering. So chaos engineering is an approach where we actually identify the failure beforehand, right? And we try to fix it to avoid the outages. we uh, we try to note down all the hypotheses. We use the experiment to break the system on purpose, and then monitor it and learn it how to fix it, so that like your system is more resilient and you won't be having like any business outages, right? So now, like after listening this, right, like you might be thinking, oh, our application is running fine. Now let's go and test the chaos engineering thingy, right? Like let's go and unplug some wires, right? Like let's shut down the EC2 instance and see like how the application is working. So I mean, it's not like I mean, it does not really work like that. Like there is always a proper approach and framework for how big enterprises like Netflix and Amazon, which actually the main companies who like started this chaos engineering model. So there is something called cloud native availability model. So the cloud native availability model basically tells you like at what layer, what all things can go wrong and what all things you can actually think of testing, right? So the first layer is called infrastructure. So in infrastructure, we basically make sure that it's highly available, right? We make sure like there is no single point of failure. And now it applies to actually your EC2 instances, basically nodes, or maybe like if you're running Kubernetes, you must be having like number of replicas. You should have like a more replicas, number of availability zones, and like multiple region, right? So that's infrastructure layer. Now the second is your switching, network and switching. So what happens is like when we design our HA system, right, like it's our application is highly available, like there might be another location of that, there is a primary and there is a secondary. If primary goes down, then there should be a smooth routing to the secondary. Like your customer should not face like any sort of disturbance if your primary goes down, right? Now when you are actually routing the customer from one location to another application actually, so you also make sure that your data application is also taking place, right? Like it's not like, okay, right now I'm saying cart one, and like in another, if I will be rerouted to another application location, then I won't be able to see cart one, right? So that data application should also take place. And then there is something called anti-entropy recovery. So if your primary location is down and your all the traffic is going to the secondary location, right? The secondary location is also like writing some data. Now like if your primary location has been like working fine, then you also have to think of like how to route the traffic back to the primary, right? So these kind of things, like we have to test it at the second layer. Now the third is like application layer, right? In application layer, like we can test a couple of things, like, and especially like since we are doing microservice based application architecture, it's easy to test, right? Like we can add latency, or we can actually kill one service, right? If you have multiple services, I'm just giving one example, right? If you are going to amazon.com and like do some shopping, right? What if they're like like identity service is not working? uh, you can just go and like try to uh, like shop something, but you're not able to say like, okay, yeah, like I'm a particular user, this is my location and all those things, like. So this might impact your application, right? And yeah, so these are the things that you can actually test. You can add latency and see like how another microservice is responding. So this is application layer. And now the last one is people, right? Like this is very important, that like we think like I'm just giving one example, right? So we have an application running in one of the server, and somehow like there was some agent, like for example SSM agent, or maybe any agent that is running on that particular server where our application is running. It does something, and like suddenly like the CPU spiked up. But at some point of time, like the monitoring system told an engineer that your application is not working. But instead of that engineer to like troubleshoot and wait, he will see like, oh yeah, it's not working, I think the CPU is high, let's just restart it and see what happens, right? We should not do that. Like if he does not have like a lot of ideas of like what's wrong with the application and like how he should troubleshoot it, he should never like reboot the server and like make things more worse, right? So there should be a people training, like in case something goes wrong in your application, right, how you should actually try to make it work, and like whom you have to approach. And also one another thing is like it's kind of like a single point of failure also. Like if you are giving only one person the task of like handling everything related to that application, that is also not good. What if he like tomorrow he leaves the company, right? So people is also like one of the like main layer of the like chaos architecture availability model. So this was the availability model, right? Now like how we actually approach towards doing chaos engineering. So we have some phases, right? So the first stage is called steady state. In this phase we basically monitor the normal behavior of system. At the same time we also monitor the business metrics. So business metric is the same thing that I said, like like if you put some latency in your application and see like how much is your sales drop, or in case like anything else. So for example, even if your Google search, right, like if you have some latency, then instead of 1,000 search per second, it will be like 500 searches. So those kind of business metrics also you have to like note it down. Then the second phase is hypothesis. In this phase, we basically note down the event occurrence result that we think could happen. For example, if the worker node of cluster goes down, the replica present in another node might be able to handle the request. So we make this kind of assumption, right? We whatever we think, right? Like okay, like if database goes down, what could happen? And during this phase, during hypothesis phase, you have to involve everybody like of that particular project. You have to involve application team, you have to involve network team, you have to involve DevOps team, because like as many questions you can ask, you just note it down. And like the third phase in design and run experiment, you actually try to do that and see like whether things are really working or not, or it was just that we thought that it will work and it's not working, right? So that's like we are doing in the third phase, that whatever we thought, like we put a hypothesis, then we will choose one hypothesis, and then we will try to do that hypothesis on our actual environment. So for example, if we are trying to the demo that I will be doing, right, it will be like deleting pods and deleting worker nodes, right? So these are the two hypotheses that I'm working on, right, that I will be doing the demo. Now scoping the experiment, like we initially we should not like test or do the disruptive actions onto the entire application, right? We have to take a small steps, like we should start testing on one services, then goes to the another services. Or for example, in case of database, instead of deleting the entire tables and all, I mean deleting the entire tables doesn't make sense, right? You have to delete one or two tables and see like okay how your application is responding. So we always have to scope the experiment. Then when you are performing this kind of experiment, like you also have to see like whether you have to notify your organization that okay, yeah, at this particular time we are doing this experiment, right? Now the fourth one is verify and learn. So whatever experiment you did and you have identified the metrics, now you have to verify that okay, whatever you thought and whatever exactly happened, is it the same thing, or like there is some differences. Now when you did the experiment, like you also have to see like whether the escalation metrics worked or not. Like for example, if there is an outage, whether it did notify like a responsible person, or like it did send an email to like the engineers who might work on the troubleshooting of the application, right? All this whether it's self-healed or not. So these kind of things is like come under the fourth phase, like verify and learn. And one more important thing, that it's more of a like a cultural thing, like in the organization, that in case like your chaos experiment somehow like you are doing and like some things goes wrong and like you thought like oh no, we did correct. I mean, don't blame the person, to be honest, because this is the whole part of chaos engineering, right? That you might have thought like it might work, but it is not working. So the main thing is like you just learn about it and then fix it, right? If you will blame the person, then it will ruin the dynamics of that your team actually. So that's one of the important part actually. Now the last thing is like once you gather all the data that okay, yeah, things are not working, we have to fix it. You have to fix it as soon as possible. You shouldn't wait for like next feature release. Yeah, I mean like if your like responsibilities allows you to fix it as soon as possible. You should fix it actually. Yep. So now, like after listening to all these phases of chaos engineering, like you'll see, like, oh yeah, it sounds cool, right? Chaos engineering, like we can actually make our application more resilient. Like we might like avoid any outages, right? Let's do chaos engineering. But the thing is, like chaos engineering is like it's not too easy. I mean, definitely, like you have to explore a lot of tools. I just now explained like there are different layers, right? Like you have infrastructure layer, application, networking layer. So you, and in the market there are tools available, right? Like you have like what was that, chaos monkey and cube monkey, right? All these tools are available for sure, like, but it does at certain layer, right? Now, like if you have to cover all the all the four layers of the model, then you have to like go for like all the tools. You have to download it, you have to install it, you have to integrate with each other. Some of them comes with the agent. You also have to maintain those agents, right? And the another thing is like whenever you are doing the chaos experiment, right, you also have to make sure that at certain point you have to stop that experiment, right? So the automated stopping of those experiment, those are the things that some tools might not provide. You have to write your own way. So uh, I mean, these were the difficulties that like generally people who are doing before they used to thought of like doing chaos engineering, like they might find this kind of difficulty. So what AWS did is like AWS provided a fully managed chaos service called AWS Fault Injection Simulator. It's pretty easy to use. I'll show in a while. You can use console and CLI, and there is no need of installing like any sort of tools or agent, except one thing that if you want something out of the box and inside the servers, then the prerequisite is like the SSM agent needs to be installed in your EC2 instance. I think that is somehow like, if in case like you are running any like servers and all, like if you are doing patching and all, like anyway, like you will be having SSM agent installed, right? Now, there is a real world condition. So there might be a scenario that like things that breaks your system will be like sequential. Like for example, there might be a scenario like CPU utilization is high, at the same time like your server is going down. So like there is a sequence, and it could be parallel as well. Like at one time, like everything is like making your application down. uh, AWS FIS also target all layers of the system. Means like it does at your infrastructure layer as well as like your network layer and application layer as well. uh, FIS have one very nice thing called safeguards. So if you let's say suppose like you are running any experiment, and what happens is like you wanted your experiment to be stopped at certain point. Let's say for example, you wanted to test auto scaling group, right, whether it is able to spin up a new EC2 instance in case like the CPU utilization is high. The moment your auto scaling group like spins up a new EC2 instance, you want your experiment to be stopped. So basically FIS have very nice integration with CloudWatch alarm. So the moment there will be a alarm, then your FIS experiment will stop. So this is like one of the safeguards in FIS. So FIS have like four components. The first one is like action. The action include the task of the experiment. So basically the hypothesis part, like for example, terminating node, DB failover, this kind of task is comes under the part of action. Now you have target. Target is like the destination where you will be performing those tasks, or you will be performing those actions. For example, terminating the EC2 instance, like which EC2 instance you want to terminate, or which EC2 instance with certain tags you want to terminate. So basically, you can actually search with the tags as well. The experiment template is something that is like a blueprint. It's a blueprint of action and target. So when we run a experiment, we are basically running experiment template, and experiment template includes action and target. So yeah, I mean, this one was a brief intro about AWS FIS. Now I will like directly jump to the demo. Um, okay, just a sec. Okay, so we have one Kubernetes cluster over here, and I'm running one application on top of that Kubernetes cluster. So there is a namespace called DSO app, and there are like 3 services running: front end, catalog, and detail. The application somehow looks like this, right? It's working fine, and I have like installed like few of the CloudWatch agent and Fluentd service so that like I could create a CloudWatch alarm. So this is the alarm, like node alarm and pods alarm. So what pod alarm says, like if your number of pods is less than 3, then it will like raise alarm. If your number of nodes will be like less than 2, then it will raise alarm. Currently, like this is a 2-node cluster. Yeah. So now let's see like how FIS looks like, right? So this is a console, FIS console, and like we have something called experiment template. So when we have to create experiment template, you can just give a description, name, and IAM role. Definitely, like basically the role should have certain permission to perform action on the target machines. Then you can create an action. Now over here, action, you can just provide a name, and you can give an action type. So over here, like these are like the predefined templates, actually, like stop instances, terminate instances. This was like infrastructure layer level, and another one is like the application level, like inject API internal error, right? You have database layer like DB cluster, reboot, failover, and then like if you want something specific that you want to do inside the server, you can write a document, SSM document, and then you can use send command actually, or automation execution. You can also use network layer stresses over here. After you select this one, for example, I just select stop EC2 instance, right? And then you will have a target. You can also I mean, like this is the first action. If you create another action, then it will ask you like the sequence, whether you want to be like sequential. If you will not select start after, then it will be like parallel at one go, like it will run all the action together. In the target, like actually let me just go to the experiment that I just created. Right over here, I created 2 action. One is delete pod, and delete pod is like it's a custom action. So I had to create a document, and then I had to provide the document ARN and the parameter. And the second action I created was like if your pod will get deleted, after that like it will delete your worker node, and then we can again check the application. uh, so now over here you can see like if I'll edit it, it will give me an option like start after. So if I'm selecting start after, that means it will be like sequential, like the first action will be like delete pod. It will delete the pod, and after 2 minutes it will go and then terminate the worker node of the Kubernetes, right? And you can also choose like the number of percentage, like the percentage of the worker node you want to down, like like if it's like 2 worker node, if you select 50%, you can also select count. uh, then you have a target. In target, you can actually mention like which resources you want to perform those actions, right? I wanted to delete pod, but where? Like, so in the document, because it's a SSM task, so I have to provide the EC2 instance ID over here. I can also provide the tags, right? When it comes to delete a worker node, like EKS worker node, over here, I can specify a node group. So based on whatever resource type you choose, it will automatically give you the target resource IDs, whether it could be a EC2 instance, or whether it could be a node group, or whether it could be a database, something like that. So and then you have a stop condition over here. Like if you are performing this disruptive action, then like at what particular condition you want it to stop. So we have this thing called like, okay, whenever this alarm raised, I want you to stop. So it will stop. The experiment will stop automatically when this alarm will gonna raise. So I wrote a simple shell script to check the status of the application. So currently, like this is like just a report like, okay, the endpoint is giving me 200. The pod status will be like 3 out of 3, and you will see like the node also like 2 nodes, right? I'm not sure like why it's slow. It should be fast, but anyway. Now I will perform, like I will start the chaos experiment over here. Just add a tag. Let's see. So it says like, like, are you sure you want to perform this experiment, right? It is basically saying like you are about to do some destructive action. So I'll just give start, and then I'll start the experiment. So you can see like the state has initiated. Click on refresh. So it's in running state now. Over here, you are seeing that the timing of these pods, like it has been spin up around like 3 hours 18 minutes ago, and at this particular time we are getting HTTP 200 okay right now. Since it's running, right, think you will see like after a certain point of time, like you won't be able to see the endpoint status because your application is not responding, because the pods are not you see like it is still loading, the page is loading. uh, Means like your pod has been gone down and your application is not responding. So at this point of time, what we should do, and now like it's working fine, and you can see like the pods has just spin up, like the timing has been changed. It has spin up like 24 seconds ago, and now you are getting your endpoint status. So this way, like you can actually do the timing calculation, right? Like at what particular time your endpoint status was like down or it was not responding, and at what time it started responding. So based on the time calculation, of course this is like like a simple shell script. If you will like create a certain you can write or stream your CloudWatch logs or those kind of things into maybe Grafana or those kind of tools, then you can actually see more better, like at what time your application went down and at what time it came up. So that will help you to monitor it or visualize it, right? Now the second thing is like, I think it would automatically go and perform the node group termination action. It is pending. So currently we have 2 nodes. It will try to terminate one of the worker node, and then we will see like whether your application is responding or not. Take some time. Okay, so this action has been completed. That means like in a while you can see that your EC2 instance would have been terminated actually. You see now it's only one worker node. Soon you can see over here as well. Or sometimes what happens is like the shell script is like not really very like written in such a way that like it's just going and like fetching the data with the TS. Like you can see like the endpoint status has been halt. That means like one of the worker node went down, and any of the pod which was running on that worker node is not responding. It will try to spin up in another worker node. So these things takes time, and maybe like your application will not be responding. Yeah, it's loading, and like over here also we cannot see the endpoint status. So what auto scaling is trying to do now, like it will spin up a new EC2 instance. It will like like add it to as a part of EKS control plane, and then like once your EKS control plane will like say like, okay, this is a new worker node, then it will start running the new whatever the pods it was running over there. So these are the things that we have to be careful when we are like designing any sort of underlying infrastructure, or we are trying to deploy any application on top of Kubernetes as well, right? You can see like the new EC2 instance came up, and it's not ready right now. It is trying to get ready. Yep. So I mean, this was the chaos experiment actually from the FIS. Pretty much this thing as a demo. I'll go back to the slides. Now, like it comes to like at what stage like we can put in CI/CD. So this is a typical like a CI/CD pipeline. We have a like development branch, feature branch. Like you have multiple pipelines. So most of the time, like you can put into a staging environment first rather than directly jumping to the production for sure. This is a standard practice that you should start doing into the first, like you should start doing at your staging environment, and then you can go for the production. The another way is like if you are doing in production, you should be very careful. Like what you can do is like you can do a canary rollout, right? And you can see over here like this is a primary and this is a canary, right? So when you are doing a canary, make sure like in 20% of traffic you can actually include the FIS injection. So what you can do is like okay, the first thing is like on Kubernetes you can do canary with AWS App Mesh. It's like a service mesh. The second thing is like when you are doing canary deployment, you every time you have to edit the file. For example, 20%, then you want to 60%, then you want 80, then 100. So what you can do is like, and these things is not automated. If you want to automate the auto rollout from 20 to 100 automatically, you have to either use step function or you can use a tool called Flagger. It's actually a very nice tool for canary deployment or blue green deployment, especially for like if your application is running in a such a way that it is using service mesh, right? So you can use Flagger. It automatically generates all the service mesh related resources. For example, your virtual node, virtual route, all these kind of files, it automatically generates for you. And another good thing it have is like it have a webhook that basically calls your any sort of testing tool. For example, your load tester. So let's say, for example, your canary deployment service B is having like 20% traffic. Like while routing the traffic, it also tests your like your application. Like okay, the load if the load is working fine, that means like okay, like let's route the traffic more. So you can consider using Flagger as well when you are doing the canary deployment, and you can use the Flagger webhook option to integrate with the AWS FIS, right? Although AWS FIS work with the like CLI or UI, Flagger use webhook as an endpoint. So you should definitely have to write like Lambda function, and then you have to put an API gateway. Then you can use Flagger webhook to call the API gateway. Then Lambda will call the FIS, and based on that, like it will give you the resources. Yeah. So, yep. Most of these details like has also been explained in my book. Actually, like how you can use Flagger or how you can use FIS. My second book, which has been launched like two weeks ago. So you can actually scan this QR code or go to this link. You can buy it. There is a discount code. I just asked my publisher to give. So they gave me like this 20 AWS. You can use this discount code to like a 20% discount. Yep. This is pretty much any Q&A. Like I'm happy to take questions. I think there might be a lot of questions I heard in the chat. Actually, let me see.
So Nikit, there's one initial question from Vijay, which Ben followed up. Basically, what Vijay is asking is, can we run this fault injection simulator in hybrid environments, like in on-premise? So yeah.
Oh, I think currently it is only running on like it is only supporting AWS resources right now. Yeah, currently it's only on AWS. Definitely, I have to check because it supports SSM.
Yeah.
And if your SSM agents are running on, but again, like it also have the role thingy, right? The IAM role thingy. So I think need to check. I think for now, I don't think it supports on premise. Yeah.
Okay.
Yeah.
From Vijay again, other than Flagger, are there any other options available?
Other than Flagger, okay. To be honest, like Flagger tool, also I explored because it does canary. I'm not sure about any another tool, but you can actually check the alternatives. I'm not sure like any another tool other than Flagger. Uh, yeah, but the good thing about this tool is like it auto generates your like the service mesh files, like which takes a lot of time to write, and in case like you are missing any sort of backend or like the service backends, then you will spend a lot of time to troubleshoot. Actually, yeah.
All right.
All right.
Any other questions for Nikit, guys? Okay. If no further questions, then
Yeah.
actually, please take note of the Google form what I have passed in the chat, so you can use it to fill in the details and for the AWS credits giveaway itself. And by the way, Nikit, thanks very much for your time in delivering this talk. It's indeed very informative. Yeah.
Thank you.
Okay. If no further questions, then I think we are winding up this event today. Thank you everyone for joining the meetup, and thanks to all the speakers who have delivered the content today here.
Thank you, everyone.